Okay, welcome to Let's Get to the Marks, going through GCSE Combined Science Trilogy paper, Friday the 14th, June 2024. It's paper two, actually. It's a higher paper. There's only 6 questions. You've got an hour and 15 minutes. What I suggest is you press pause at the start of each question, grab a pen, grab a bit of paper, have a go at the question, try and write down bullet points, some answers, so you make the revision active, and then unpause and watch the explanation. All right, let's go. Question one, a teacher demonstrated how the frequency of a wave on a string affects the wavelength of the wave. Figure one shows the equipment used. So we've got some masses here on a pulley with a bit of string. It's attached to something called a movable wooden bridge. We've got a meter ruler here. We've got the wavelength of the string, and the string seems to be attached to a vibration generator, which is attached to a signal generator, which has the number 45 written on it. The frequency of the signal generator is adjusted, so the wave shown in figure one is seen. So they've adjusted this until this gets to a number where you can see this wave perfectly like that. At this frequency, the string vibrates between these two positions. Describe a method the teacher could use to investigate how the frequency of the wavelength, how the frequency of the wave affects the wavelength. This is worth 4 marks. Why don't you pause the video, have a go, see if you can make 4 bullet points about a method to investigate frequency and how that affects the wavelength. Okay, I'm going to go through the answers. So essentially what we want to do here is we want to keep the masses the same. We're not changing mass. It says nothing about changing mass. What it does say is change the frequency. So to change the frequency, this will cause vibrations, which change the frequency. The amount of vibrations per second is measured in hertz. This is 45 hertz. So you might want to do the first test there, and then you might want to do 4 other different frequencies. So we want to say, use the signal generator to change the frequency. Now, we want to get it to a position where this is actually vibrating. We want to get it to where it's moving so you can just see a steady wave, the full down and up. And then you know that's an entire wavelength and you can measure that against the meter ruler. So use the meter ruler to measure the wavelength when we change the frequency. Now, for each of these, you're going to have to move this movable bridge. You're just going to move it a little bit until you get the full wave. Because when you change the frequency, it may affect this. So you'll need to move this until you get another wave pattern just like this, but at a different frequency. And at that point, you stop and you measure the wavelength. So you may have to move it forwards or backwards in order that you can see a full wave. And that's what we need to put down in writing. So let's go ahead and put that down. So I'm going to start by saying, um, use the ruler to, oh my days, I'm writing in white. Oh my gosh. Use the ruler to measure the wavelength. Um, then adjust the frequency on the signal generator and move the wooden bridge until a new stationary or non-moving wave is seen at this frequency. Then measure the wavelength and record this. What do we want to say? Oh, we should say keep the masses of weights the same and repeat 3 times and take a mean wavelength at 5 different frequencies. Bosh. So essentially, we're just saying we're adjusting the signal generator. That's going to get us a mark saying that in order to change the frequency, use the signal generator, use a ruler to measure the wavelength. You want to repeat 3 times at each different frequency and find the mean. So we're going to use 5 different frequencies. Control variable, keep the masses the same. Yeah, we've already said measure the wavelength. Move the wooden bridge until you see a new. How do you know you've got to? Well, you need to see a new stationary wave. The thing is, the string will be vibrating. Oh gosh, that's on a color. The string is going to, what do I mean by a stationary wave? The string is vibrating like this. You want to get it till it's vibrating so fast, but you can clearly see two kind of waves, whatever. They're out of sync, so you'd see 2 waves in sync, but I'm not going to bother drawing that again. Yeah, clearly see a wave. It'll appear like the wave's not moving. It'll appear like you have a solid bit of string bent like that, but it's actually just at that frequency where it appears you have a stationary wave. Okay, let's move on. Right, 1.2. Which equation links frequency, wavelength, and wave speed? You can look this up on your equation sheet. So this is a free mark, absolute bonus. See if you can have a go from your memory. Okay, I'm going to go through the correct answer. So the wave speed, where are we, is equal to frequency times wavelength. So the correct answer is here. You get the wave speed by doing frequency times wavelength. Lovely jubbly. Now they're going to get us to apply that equation. So really, I call this a free 4 marks because they've gone and you can look on the equation sheet and find that equation. And now this is another 3 lovely marks. The wave on the string has a frequency of 45. The wave speed is 35.1. Calculate the wavelength. There isn't a rearrangement to do here, but our units are all perfect. Frequencies in hertz, not kilohertz or megahertz or millihertz. And speed or velocity, wave speed is in meters per second. So that's all perfect. So we said that V equals F times the weird wavelength symbol, that one. Was that lambda or something? So what we're going to do now, we need to rearrange this equation to make wavelength the subject because it says calculate the wavelength. So we can do that by dividing both sides by the frequency so that we get V over F equals this, and that is going to get you your 1st mark rearranging that. Now it's to put the numbers in. So we're going to go 35.1 divided by 45, and that is going to give us our wavelength. And we need to smash that in the calculator. Hold on, I've got my dodgy phone calculator. Let's have a go. 35.1 divided by 45. And that equals a wavelength of 0.78 meters. And that's going to give us 3 marks. So correct rearrangement, correct insert in the numbers, no diddy. And then the correct answer, 3 marks. Absolutely beautiful. Let's move on. Right, question 2. Figure 2 shows an Olympic gymnast performing a floor routine. Whoa. The floor contains springs. When the gymnast lands on the floor, a force compresses the springs, squish, into the floor. When a spring is compressed, the elastic potential energy of the spring increases. Explain why compressing springs in the floor helps the gymnast jump higher. Use ideas about energy in your answer. So what they're asking you to do, and you're going to pause the video in a second, have a go, is when somebody lands on the spring squishes down. Why does this then enable the gymnast to go higher? You've got to use the words energy, and you want to talk about the specific energy transfers taking place. There's my clue. Pause the video, have a go. All right, I'm going to go through the answer. So when she squishes down on the spring, or when the gymnast squishes down on the spring or compresses it, what does the spring gain? So the compression, and you don't need to write these words, but the compression of the spring, it gains elastic potential energy. As the spring extends or whatever, yeah, let's say extends, that's the opposite of compress. So as the spring extends, what is the elastic potential energy converted into? The elastic potential energy is converted into kinetic energy and then gravitational potential energy, enabling her to go higher. So as the spring extends, that energy is converted into kinetic, which moves her up into the air, and she gains gravitational potential energy. So we just talked about the energy transfers that take place. When the gymnast lands on the floor, one of the springs compresses by 1.2 centimeters. The spring constant is 8,500 Newton meters, or Newton per meter. Calculate the elastic potential energy stored in the spring. Use the physics equation sheet, give the unit. Again, this is beautiful 4 marks. We get to use the physics equation sheet. So let's go. Okay, first things first, we want to select from the equation sheet the correct equation. So give me a second while I grab the equation sheet. Okay, so looking down this equation sheet for GCSE Physics for AQA, you can see all the equations you need. And look at this one. Elastic potential energy equals 0.5 times the spring constant times the extension squared. So we need to, that's EE equals half KE squared. So we're going to memorize that. We're going to go back and write that down, rearrange it, and get our 4 marks. Let's go. I don't know what I'm doing here, folks. All right, we're back. We're back. When the gymnast lands, let's write down the equation. It was EE equals 0.5. Oh my gosh, I've already forgotten it. What was it again? Let's zing back. I need to zing back because I've already forgot 0.5 ke squared. Jeez. So elastic potential energy is half times the spring constant times the extension squared. So we need to just put our numbers in and convert our units. Now, one thing to note straight away, we are calculating elastic potential energy stored in the spring. We've used the physics equation sheets. We've selected the correct equation. These are the numbers we've got. Why don't you pause the video, have a go, and then I'll go through. All right, I'm going through the answer now. So the elastic potential energy is half times K. So I want to set this out. So EE, and that's what we're going to calculate, so we don't have to rearrange, is half 8,500 times the extension, which is 1.2. I have an issue here, that's in centimeters. And in physics, anytime you get length, distance, or height, they're in meters. Distance is always in meters, and 1.2 is a distance. In this case, it's extension, but it's supposed to be in meters. So I need to turn centimeters into meters. So I'm going to do, oh, sugar, I don't really need to put the unit there. I'm going to do 1.2 divided by 100, because we need to put that in meters. And then we want to square that. So now what I need to do, folks, is rearrange this lovely equation. So it's a little bit harder than the last one, but we've probably got a mark already for putting the numbers in. So before you rearrange the half times 8,500, so let's do that. We go 0.5 times 8,500, oh my days, 500. So I end up with 4,250 times 0.012, and I need to square 0.012. So let's go 0.012 times 0.012, or squared. So we're going to go 4,250 times 0.000144. So let's times 4,250, and that equals 0.612, and that's the elastic potential energy, 0.612. Now what I want to know is, what's the unit for energy? Well, the unit is joules. So how are these marks awarded? You're going to get a mark for writing out the rearrangement of the equation. You'll get a mark for converting 1.2 into 0.012, even if you flop the rest of it. Converting that into meters gets you a mark. If you didn't and you kept it as 1.2, you only lose 1 mark. You get error carried forward. You can get the other 3. And then 1 mark for coming up with the answer, 0.612, and 1 mark for the units, joules. Wunderbar. Let's move on. When masses are placed on the spring, it compresses. The student measured the compression of the spring for different masses. Figure 3 shows some of the equipment used. We've got large masses, we've got a scale, and we've got a spring. Describe how the compression of the spring could be determined. 2 marks. So if I want to find out how much the spring is compressed, I can use these weights and this scale. What do I need to do? Pause the video, have a go. Okay, so what we're going to want to do is, before we've added any weights, what we want to do is we want to measure the original height of the spring. So we're going to measure the original height, we might call it length, of spring before adding masses, right? So make sure you measure the original height before adding masses, keep the ruler straight, etc., etc. Then we can say, then add a mass and measure the new height of spring. So we're going to now measure the new height of the spring. But this is not all of the marks. So this is going to get you a mark. Measure the spring before and after adding the weight. However, this is not all of the marks. What we need to do now, we've got our spring with our weight on. We want to know how much has it compressed. So we need to work out how much it went down by. So we're going to say subtract the new length, subtract the new height. I'm using the word height. You could say length or whatever. Subtract the new height from the original to find the compression. Okay, how much did it go down by? And that's how you'll find the compression. There you go. Righty ho, let's move on. 2.4, explain why the investigation should be done on the laboratory floor rather than on a table. So why do we want to do it on the laboratory floor rather than on the table? Now, this is the kind of one I'd probably lose my marks. I'd probably start talking about gravity and, oh, yeah, the gravity's lower on the floor and the gravitational potential energy. But really, they're just talking about safety here. And so don't beat yourself up if you've lost the marks, because you might be so in tuned with your physics that you start waffling about the wrong thing. actually, this is just about safety. Why is it not so safe to use weights on a table? So on the floor, the weights uh, are less likely to fall on your foot and cause an injury. So it's pointing out the hazard and then the risk with it as well. So the risk is that you're going to get an injured foot, right? Um, let's go down. We've got the results of their experiment. So this is the force or the weight, the masses, which they've converted into force that they put on the spring. And this is how much it's squished down, which is the compression. And here they have done the Y and X, changing Y over X. So the spring constant is the gradient of the line of best fit. Determine the value. So this is just reading the graph. So we need to read the graph carefully and then determine the spring constant and give your answer to three significant figures for 2 marks. So it should be nice and easy. We just want Y and X. Let's go and do that first of all. You could pause the video now and have a go. I've enlarged it for you. No diddy. Let's go. Okay. So let's work out Y. We kind of need to work out the scale, don't we? If we're going to work Y out, we need to know what this scale is over here. And you have the value is 100. And how many squares? There are 10 squares. So we want to do 100 divided by 10 equals. So each square is worth 10. Each square equals 10. And because of that, we can now work out the size of this. So we've got 5, we've got 1, 2, and then we've got 10 there. That's 12. And then we've got 22, 23, 24, 25. So we've got 25 squares times 10, we've got 250. So Y equals 250. Now let's work out what X is. And again, what you want to do here is check the value. It's 0.01 because we go 0.01 to 0.02 and it's divided by 10. Ugh, ugly. 0.01 divided by 10. So this is a little bit more difficult. This is 0.001. Each square is 0.001. So what you can do, you can mash that in the calculator or you can just check this out. So this goes from 0.01 to 0.05. So that's pretty easy. That's 0.052, so that's not bad at all, actually. That one was the way they drew it nicely where we didn't have to work too much out. So it's 0.05. No, that's 1, 2, 3, 4. I tell a lie. Tell me lies, tell me sweet little lies. Right, let's go like that. It's 0.042, that is. So, why? Because we don't need to include this. This is not part of the graph. So it's really 0.01, 0.02, 0.03, 0.04, and then 0.042. Okay, coolio. So what we need to do now, that is going to get us 2 fat marks for working that out. Bosh. And then what we're going to do is remember those numbers. And we're going to go down, determine the values. We've done that. We smashed out the 2 marks. Now it says determine the spring constant. So we need to find the gradient. Well, gradient is always change in Y. This triangle stands for change over change in X. So we want to do 250 over 0.042 and give your answer in 3 sig fig. So we're going to go 250 divided by 0.042 equals, oh my good gosh, equals 5,952. What the? What the? So what we want to do here, we've got 5,952 and we need to round this to 3 significant figures. So I'm going to go with 5,900 and we're going to keep it at 50. And why? Because this 2 is lower than 5, so we're going to take that down, and it's your first 3 numbers, so 5,950. The 0 doesn't really count, so we just want to represent like that, and that's going to get us 2 bad boy marks. Oh, the end of question 2. Right, let's go to question 3. So what have we got here? Electromagnetic waves are grouped according to their wavelength and frequency. Electromagnetic waves are transverse waves and can travel through a vacuum. Give one other property that is the same for all electromagnetic wave. All types of electromagnetic wave. Jeez, I can't read. Okay, so what else do we know? They're grouped according to wavelength and frequency. They're all transverse. They can all travel through a vacuum. Guess what? There's 4 things. Can you think of some of the things that all waves can do? Well, it says all types of electromagnetic wave. I wonder if we can just say a property that is the same for all waves. So there are like 4 properties or 5 properties that all waves can do. Think about when they change medium at an angle. Think about when they hit a plane mirror. Um, think about what happens as like light goes from air through a glass block. What happens to some of that light? Oh, yeah. So here are the answers I would give. I'd say they can be absorbed, they can be transmitted, they can be reflected, they can be refracted. So these are all things that can happen to waves. They can all be absorbed, they can all be transmitted, which means pass through an object, a transparent object. They can all be reflected off a smooth surface, and they can all be refracted if changing. They can all be refracted at the boundary of a medium if changing from two different densities. You get the idea, Cooley. Oh, let's give ourselves a mark. Right. What is meant by a transverse wave? Sometimes this is two marks rather than one mark, but it's probably easier to get the mark like this. But essentially, you've got two types of wave. You have longitudinal waves and transverse waves. Why don't you pause the video, see if you can remember the definition? All right, I'm going to go through it. So the definition of a transverse wave is this is a wave and it's going from point A to point B. Then it causes the particles that it goes through to oscillate, which is a funky name for vibrate, up and down, perpendicular, or across the direction of the wave. So we're going to put that as our answer for transverse waves. So causes oscillations. By the way, you can use vibration here. It means the same thing. Causes oscillations perpendicular to the direction of travel of the wave. You can just say the direction of the wave. So oscillations are perpendicular. Now, if you were doing a longitudinal definition for the longitudinal wave, like sound waves, you just need to change that word perpendicular to parallel. So it causes oscillations parallel back and forth to the direction of the wave. This is oscillations perpendicular or up and down across the wave. Okay, let's go. Which group of electromagnetic waves is used for satellite communications? So, communications, we can use infrared, we can use radio waves, we can use microwaves. Now, one of those is good because it can penetrate the Earth's atmosphere and reach the satellites. And the other way down, the satellite can send that wave back down, which will penetrate the atmosphere. What you don't want is something like a radio wave, which could bounce off of the atmosphere, certain frequencies of radio waves. So, we're going to go with microwaves. And microwaves have just enough energy and a high enough frequency, slightly higher than radio waves, where they can penetrate through the Earth's atmosphere and reach satellites. Okay. 3.4. Visible light is the only group of electromagnetic waves that the human eye can detect. Which color of visible light has the shortest wavelength? So what you've got to do here is, if hopefully you know your electromagnetic spectrum off by heart, you can pause the video, have a go, guys. Right, I'm going to go through the explanation. So we have radio waves. What is it? Microwaves, infrared waves. Oh my gosh, radio waves, microwaves, infrared waves. I'm losing the plot. Visible light, UV, X-ray, and then gamma. Hopefully I haven't missed anything out. So we're just looking at the visible light. Now you can see we have a large wavelength by radio waves and a short wavelength by gamma. So as we go across the spectrum, the wavelength is getting shorter and becoming higher frequency. Well, what's the first color in the rainbow? The first color in the rainbow is red, then orange, then yellow, then green, then blue, then indigo, and violet. Richard of York gave battle in vain, or Roy Gabiv, however you want to remember it. So which one has the shortest wavelength? The smallest distance between the peaks, that's going to be violet. So as you go towards the blue end, you're looking at high energy, high frequency, short wavelength waves. If you see a fire that's burning blue, you remember your blue Bunsen burner flame, right? That is really hot. If you see a red or orange Bunsen burner flame, it's still hot, but it's not quite as hot as that blue flame because it has a longer wavelength, lower frequency, so lower energy. So anyway, folks, blue is the color with the shortest wavelength. Give yourself a pat on the back if you got it right. Sorry, violet. Oh my days. Give yourself a punch in the face if you got blue, and give yourself a pat on the back if you got violet. Nice. 3.5. The highest rewind. The three highest frequency groups of electromagnetic waves are hazardous. Describe a risk linked to each group of high frequency electromagnetic wave. So what are the three highest frequency groups? So if we just zing up my thing again, we got UV, X-ray, and gamma. So what we want to know is a risk linked to each of these. So I'm going to say ultraviolet light, what's the risk? Equals skin cancer. We could put sunburn, that would be good enough. Violet, ultraviolet light or UV light, you can get skin cancer. X-rays, again, they're highly ionized, ionizing, and again, cancer. And then we can say gamma rays equals also cancer. So you can see that all of these can cause cancer. So that's the main risk linked with all of these groups, as they are highly ionizing. So they are ionizing types of radiation, which is why they're hazardous, and all of them can cause cancer. Okay. Figure 5 shows a person using a mobile phone to allow a laptop to access the internet. Mobile phone, laptop. So they're doing that, the old hotspot. Electromagnetic waves emitted by the mobile phone send information to the laptop. The electromagnetic waves emitted by the mobile phone have a period of 4 times 10 to the minus 10 seconds. Calculate the frequency of waves, use the physics equation sheet, and give your answer in standard form. Lovely. So what we're going to do is smash on over to the physics equation sheet and let's have a little look. Okay, they mentioned time period or period, and you can see 1 over frequency equals the time period. Let's take that equation back and see what we can do. So, bada bada bing. Right. Calculate the frequency. So we had 1 over the frequency, 1 over f is equal to the time period. Well, all we've got to do is rearrange this and do 1 over t. So we're going to go 1 over t equals f, and that's going to get us our first mark. Now we just need to smash in the digits, and we're going to do 1 divided by 4 times 10 to the minus 10. And your calculator will probably put this straight into standard form for you. And if not, you can just press SD on your calculator and it will do. And your answer is going to be something like 2.5 times 10 to the 9, like that. And that is going to be your answer for 3 marks. So you're going to get 1 for that, 1 for putting the numbers in, and 1 for your correct answer in standard form. All right, let's zing down, zing down, zing down, zing down. 3.7, the electromagnetic waves are produced by oscillations in the transmitter of the mobile phone. Explain how oscillations in the transmitter enable information to be transferred to the detector in the laptop. So you've got your mobile phone over here, and you've got your laptop over here. What they're saying is, how do vibrations over here, explain how oscillations in the mobile phone, little vibrations in your mobile phone, allow information to be sent to the laptop. Why don't you pause the video, see if you can write 4 bullet points, then unpause and watch the walkthrough. Okay, so over here in the mobile phone is a transmitter, and the transmitter converts vibrations in the mobile phone, vibrations, it converts into a radio wave, and that radio wave comes over to the laptop and hits something in the laptop called a detector. Now, the detector in the laptop converts those radio waves into electricity. That's supposed to be like a lightning bolt. That is the worst electricity sign ever. And yeah, let's put that all in words. So we're going to say the transmitter in mobile phone converts oscillations into radio waves. The radio waves hit the detector in laptop, in laptop, in laptop. So, oh my days. There we go. And what happens once they've hit the detector in the laptop? The detector converts the radio waves. They cause the detector to vibrate, essentially. So let's say this causes the detector to oscillate, and these are converted into AC current. I can really just say AC because AC stands for alternating current. It's kind of like a double. I hate this, but you write AC current, you're basically saying alternating current. Bit weird, eh? Right, converted into AC or alternating current. I could just write alternating current. That would be better. Um, which is at the same frequency as the radio waves. Okay, and that's going to get you all 4 marks. And what does this essentially mean? It means that the mobile phone vibrates at a particular frequency. Let's pretend it vibrates at 30 hertz. So it vibrates 30 times a second. A little thing inside the mobile phone moves side to side 30 times a second. That then creates a radio wave with a frequency of 30. That radio wave goes across to the laptop. Obviously, the frequencies are going to be completely different than this, but the frequency of that radio wave, it goes across to the laptop and causes the detector to vibrate at 30 times per second. And that vibration is then converted into current, electrical energy. It's converted into current, and that current has a frequency of 30, which was the same as the radio wave. So this just showing you how it starts off in the phone via vibration. It's converted into a radio wave. The radio wave can travel through the air, hit the laptop, be converted back into a vibration that vibrates, a transducer, something that transforms that kinetic energy into electrical energy and current with the same frequency. Now, what do we get the 4 marks for? Saying that the oscillations are converted into radio waves, saying that the radio waves reach the detector, which cause the detector to oscillate or convert into current with the same frequency as the radio waves. Wunderbar. Oh, we're on question 4. At long last, it's taken forever. Figure 6 shows 2 magnets in a wire. There is current in the wire. Okay, a force acts on the wire. What is the direction of the force on the wire? 1 mark. Is this multiple choice? Let's have a little butchers. Into the page, out of the page, to the left or to the right. Why don't you pause the video, have a go at this, see if you can work out, does the wire move into the page, come out of the page, or go left or go right? And then I'll go through the explanation. All right, I'm going to go through it. So, of course, I'm going to long out my explanation because we love that. Right, north to south, you have a permanent magnetic field like this, okay? And we get movement because of something called the motor effect. And essentially, as current flows through the wire, a temporary magnetic field forms in concentric circles around the wire. And this clashes with this permanent magnetic field of the magnet. Okay, you say, wunderbar. But what do we have to know? So here, this arrow represents the direction of the current. So my current is going up. We know the magnetic field always goes north to south, so that's going that way. What we have to do here is use our left-hand rule. And this is the left-hand rule. So sometimes they ask you to explain how to use it for like 3 or 4 marks. It's actually easier because you just have to name what each finger is. So your thumb is movement. So we're interested here in where our thumb points. That's going to give us our answer. This is magnetic field, so north to south. So line up that finger with north to south, just like that. And your second finger here, this is current. Okay, so right now we're not in the correct orientation. What I want you to do is get your hand like that and then rotate your hand a little bit this way. So put your hand like that, then turn it halfway this way so that your second finger points up in the direction of the current here. And now it's going to look like, oh, check out this incredible art. It's going to look like this. Your second finger is going to be going up, the current finger. Your magnetic field is still going north to south because it's got to be in line with this north to south. Which way is our thumb now pointing? Our thumb is now pointing into the paper. So our second finger will be pointing up because you've rotated it round. That's the current. The north to south is pointing in the same direction it was at the start, which is left to right, but now your thumb is going into your laptop screen or into the page. So the answer here, folks, is into the page. And that will get you a mark. Wunderbar. Yeah. Right, let's move on. 1 mark for using the left-hand rule. That's fine, but sometimes they give you a whole. You get 3 or 4 marks for using the left-hand rule, and they'll say, explain how you know the direction. I prefer that because if you can't work out the direction and twist your hand around like a gymnast, then you can still get the marks for saying the thumb is movement, the first finger is magnetic field, and the second finger is current. Align the current and the magnetic field up, and wherever your thumb points is the answer. So sometimes make sure you know how to explain what you would do. It's kind of easier than actually doing it. The length of the wire in the magnetic field between the magnets is 80 millimeters. The current in the wire is 4.6 amps. The force on the wire is 0.092 newtons. Calculate the magnetic flux density between the magnets. Use the physics equation sheet and give the unit. 4 marks. You gotta love physics, people. Right. Let's bus over here. And we're going to find that here, number 8, force on the conductor is equal to carrying a current equals magnetic flux density times current times length F BI, F bill, F bill. Let's go. Right. So we want this equation, F equals bill. Lovely jubbly, Billy. Okay, what do they want us to find? That's the most important. The magnetic flux density, that is the B. So they want us to find B. So we want to rearrange this for 1 mark. So I'm going to go, I want to get rid of the I times L. So I'm going to divide both sides by I and both sides by L and leave the B on its own. So we're going to have F over I times L equals B. Let's put the numbers in for another mark. So rearrangement's going to be a mark. Let's put the numbers in for another mark. So we have 0.092 newtons. We're going to check, is that kilonewtons or anything? No, newtons should just be N. We don't need to convert. And we're going to divide that by I, which is the current, 4.6 amps. Amps is perfect. Watch out if they put a little M in front of it or something. Little m is milliamps, big M is megaamps. You need to convert into amps from those positions. And we have 80 millimeters. So yes, they have given us a conversion. What did I say earlier in the test? Height, any length, any distance, anything you'd measure with a ruler or a tape measure must be in meters. So we need to convert this into meters. So we're going to do 80 over 1,000. And we're going to get, what is that? 0.080, I believe so. So we're going to get times 0.080. Let's just double bubble. Doesn't harm to double check your maths, even when it's the simplest maths. So let's just do 80 divided by 1,000. It's 0.080. So now we're going to smash this in the calculator and we're going to get our answer and we're going to go, beautiful, smash up the marks. And you probably won't remember the units for magnetic flux density, but let's give it a go. 0.092 divided by 4.6 times 0.080 equals 0. Whoa. Figure 7 shows an electromagnet close to a permanent magnet. Here's an electromagnet. We've got an iron core surrounded by a coil of wire. We've got a power supply. We've got a switch. We've got a permanent magnet. Let's read the questione. The electromagnet exerts a force on the permanent magnet. The permanent magnet exerts an equal and opposite force on the electromagnet. Which law is this an example of? So you've got Newton's 3 laws. They're testing you on those laws. I'll go through each of the laws for you, but pause the video, see if you can find the right box, the right answer, equal and opposite. And yeah, the correct answer is Newton's third law. He actually said every reaction has an equal and opposite reaction. Um, so that's the same one. Every yeah, equal and opposite force, two objects interacting with each other have an equal and opposite force. Newton's first law, that is that an object will not change its direction or its shape unless you have unbalanced forces operating on it. Newton's second law is the force equals mass times acceleration, kind of the inertia thing, like which just basically explains that um, if you want a bigger mass to accelerate more, you need a bigger force. It's just that F equals ma, I think of that. So you're always going to use F equals ma to explain the second law. And then the third one is just that two objects interacting equal and opposite forces business. Right, let's move on. 4.4, give two changes to the electromagnet that would increase the force on the permanent magnet. Basically, how can we make this electromagnet stronger? It's already got an iron core. What could we change? Look at this diagram. What could we change to make this have a stronger attraction to that magnet? Pause the video, have a go. Okay, the two things you could change, you could increase the turns in the coil. Now, if you say increase the number of coils, they might be generous, but this whole thing is called a coil. We call these spins of wire turns. So you should really say increase the number of turns of wire. And then, of course, we can do something to the power supply, which is increase the voltage or increase the current on the power supply. Okay, so we're going to put those as our two answers. So increase number of turns, increase turns in the coil, increase the current or voltage in the power supply. Now, it does say give two changes to the electromagnet, so I don't think they would accept move them closer together. If we move them close together, that would increase the force. Maybe they'd allow that, but is that a change to the electromagnet, moving it closer to the permanent magnet? I'm not sure. But these are your best answers. Right, let's go. 4.5, give two changes to the electromagnet that would reverse the direction of the force exerted on the permanent magnet. So what they mean here is instead of attracting, it would push the permanent magnet away. So how could we reverse the direction? So let's go study the diagram again. Okay, guys, see if you can study this diagram and see how we can make the force, instead of the force going like that, let's see how we could change the direction of the force. Why don't you pause the video, have a go? All right, I'm going to go through the answer. So we can do something with this power supply. We can reverse the connections. Let's imagine it's plus minus. We can flip it round so that the connections go the other way. And this will reverse the direction of the current and therefore reverse the poles of the electromagnet. And the other thing we could do is reverse the coil um, direction around core. So we could reverse the way the coil is wrapped around the core. You could say reverse the power supply or reverse the connections on the power supply. Yeah, we've already done that. Or reverse the coil. Yeah, we'll go for those two. Okay. Right. Question five. A safety test was carried out to determine how the speed of a car affects the stopping distance. At the start of the test, the car was moving slowly. The car accelerated at 5.8 meters a second for 2.5 seconds. The final velocity of the car was 20 meters a second. So the car accelerated at 5.8 meters a second for 2.5 seconds. The final velocity of the car was 20 meters. Calculate the initial velocity of the car. Use the physics equation sheet. Acceleration equals change in velocity divided by time. I'm tired now. All right, acceleration equals change in velocity divided by time. So we know that at the start of the test, the car was moving slowly. The final velocity, calculate the initial velocity. So what we have really is A equals final velocity V, take away initial velocity over time. So we really just need to rearrange this equation to find U. So what we can do first of all is times both sides by T. So we're going to get A times T equals V minus U. We can then, um, oh my good gosh, we can take away V from each side. So we end up with A times T minus V equals minus U. Do that if we like. That's one way to do it. I'm sure people would do it another way. Right, acceleration A is 5.8. The time is 2.5. Yeah, that's time. And then minus U, what was V? Sorry, minus V was 20. Oh my days. What does this equal? 5.8 times 2.5 equals 14.5 minus 20 equals minus 5.5. Obviously, that's minus U, so U must be 5.5. What a weird way to do it. And I'm looking for fat marks. So we're going to units. No, that's all good. 5.5 up in meters per second. Is the initial velocity of the car. So one mark for rearranging. We'll get the final answer, we'll get another 4 marks. I mean, a more sensible way to do this, which doesn't involve rearranging it like that. Okay, that way was fine as well. But a more sensible way would be to go like this. A equals V minus U over T, wunderbar. Let's do A times T equals V minus U. So we do A times T, which is 5.8 times 2.5, and we get, what was it, 14.5, and that is equal to V minus U. So we go 14.5 is equal to 20 minus U. So then what we could do is we could just add 20 to each side or whatever, and we get, no, sorry, take 20 away. Oh, it's the same thing. Yeah, whatever. You get the idea. You just go 20 minus 14.5 equals 5.5. God, I'm talking myself around into circles there. Oh my good gosh. I need a coffee. The reaction time of the driver was measured. How can the reaction time of the driver be used to calculate the thinking distance? Well, we know the velocity. So if we know the velocity, we know that velocity or speed equals distance divided by time. So if we go speed or velocity times time equals distance. Lovely jubbly. So we want to multiply the reaction time by we want to multiply reaction time by the speed, and we'll get the distance. All right, that's going to get us a mark. Let's move on. Oh my gosh, I'm putting ticks on the page. The car, not a graph. Oh my God. This car was driven at a constant speed. The driver applied the maximum braking force and the braking distance was measured. The test was repeated at different speeds. Braking distance in meters. Oh my God, this graph is like dun dun dun, so big. Speed, no did he equal what the hell? Speed in meters per second. Right. Oh my gosh, that's too big. Braking distance and speed in meters per second. 5.3, which of the following gives the relationship between speed and the braking distance? Braking distance is equal to 1 over the speed. Braking distance is equal to the speed. Braking distance is equal to the speed squared. Oh, well, we can just check it out on the graph, right? So is braking distance equal to speed? Well, let's check it out. Braking distance is 12, and we go across on the graph. No, this is 11, baby. So we can get rid of that middle one. This one is definitely not right. Braking distance, is the braking distance equal to 1 divided by the speed? Well, let's see. So um, when the braking distance is 2, oh my God, that's too complicated. The speed is like 4.6. So if we go like 1 divided by 4.6, do we get 2? No, we get like 0.2. So no, the braking distance is not equal to that. But what we can say potentially is so we can get rid of that. So this leaves our only answer as braking distance is equal to the speed squared. Let's move on. 5.4, during one test, the brakes were applied with a force of 6,250 newtons. The deceleration of the car was 5 meters a second. The braking distance of the car was 14.4 meters. Determine the momentum of the car before the brakes were applied. Use the physics equation sheet. This is going to be quite foul and disgusting, and it's going to need more than one equation. So we've got the force. So the thing to identify with these 6 markers is what equation do you need to use from the equation sheet? We've got force, we've got velocity, and we've got distance. During one test, the brakes applied with a force of that. So what I really want, and then we've been told momentum. So I want to see, is there any equations? I really need two. I know you're going to need 2 equations because it's 6 marks, but we've got force, velocity, distance, momentum. Let's go check out the equation sheet. 6 marks. You normally need to use at least 2 equations to do this, but for this one, you actually need 3 equations from the equation sheet. Just identify what you've been given. That's always the clue. And look at any equation you can use to find something out with this data and apply it. And that will get you some marks. Why don't you pause, see how many of the 6 you can get? All right, I'm going to go through the explanation. So we're going to look at this. We've got 6,250. That's a force. And we've been given the distance. And we've been given acceleration or deceleration, same as acceleration. We've been asked to find momentum. Well, let's go to the equation sheet. This is an equation sheet from the school, but it has all the equations you need. So you'll get these in your exam. So momentum equals moment. No, we don't want that. Distance. No. Acceleration is changing velocity over time. Here we go. Momentum equals mass times velocity. So we need that in order to work out the momentum. We're going to need, which means we need mass times velocity. Yeah, we haven't been given either of those. So we need to work out mass and velocity in order to find this. Force equals changing momentum over time taken. What else? What else? Final velocity minus the initial velocity. So we can find out the initial velocity, and we can do 2 times the acceleration, which they gave us, and they gave us the distance. Great. We've been given force though, and force isn't there. What is the one with a force? Force. Resultant force equals mass times acceleration, F equals ma. Okay, so I think we've got all the equations we need. So we've been given the force, we've been given the acceleration. We need to calculate the momentum. Looking from the equation sheet, momentum is P equals m times v. I know it's a pain, but P is momentum equals mass times velocity. So we're going to start from that point. We need to calculate the momentum for 6 marks. So the first off, we can calculate the mass. We can do the mass by doing F equals m times a. Now, what does that stand for? That is force is equal to mass times acceleration. And guess what, folks? We've been given the force F and we've been given the acceleration A. So in order to find the mass, we've got to rearrange and we can do force divided by acceleration equals the mass. So I'm going to do 6,250 and divided by 5. So let's go. 6,250 divided by 5. And if you only get this far, I think you haven't done too bad. 1,250. So we have our mass is 1,250. So we now know the mass, that is kgs. And you can see the units here are kg meters per second. So now we need meters per second. We've got the kg bit. We now need meters per second. We've probably got 2, possibly 3 marks from that. And even if that's how far you've got, you're still doing good. We've now been given distance and we still have acceleration. Well, there is an equation, the linear acceleration equation, and it goes like this. V2 minus U2, or is it U2 minus V2? Oh God, right, equals 2AS, where S equals distance. So a little bit unusual because normally we use D. I don't know why for this equation they use S. There's probably a reason, but I'm not aware of that reason. Some degree level physicist person can tell you that. A physicist. So V minus U squared equals 2AS, where S equals distance. So all we need to do here is we've got the acceleration, we've got the distance. So we are determining the momentum before the brakes were applied. That's U. We want the initial velocity because that's what's going to give us our initial momentum. So we want U. The final velocity is going to be 0, right? Because the car stopped. So we know that V is going to be 0. So we can just write this as U squared is equal to 2AS. Why can we do that? Because we know the final velocity is 0 because the car's braking. So its final velocity, it has stopped. So now all I need to do is go 2 times 5, which is the acceleration, times the distance of 14.4. And that is going to give me 140. But remember, that is U squared. I actually need to square root that so I can get U. So, and if I do that, I'll find the initial velocity was 12 meters a second. This was the hardest part of this question, was working out that we needed to use that linear equation for acceleration. So now we know that it has 12 meters a second. We know that we just need to do M times V. So M times V, so 1250 times 12 equals 15,000. And what is 15,000? That's P, that's momentum, and that is kilograms times by meters seconds. And bosh, that was a hard question. So get a couple of marks for that bit. You get a couple of marks for that bit. Maybe 3 marks for that bit, I feel like, but you might be able to get 3 from that and 2 from that. That would be nice. And then 1 from that bit to get that. There we go. Right, let's move on. Final questiones. Has it been difficult? Absolutement. Question 6. Rockets that have been developed so that people who are not trained astronauts can pay to travel to space. Figure 9 shows the passenger module and propulsion module of a rocket. The propulsion module burns a large volume of fuel. Okay. The rocket was initially stationary on the ground. That means we're not moving 0 meters per second. The rocket accelerated upwards until it reached a height of 40 kilometers. The constant acceleration of the rocket was 6.48 meters per second. Calculate the velocity of the rocket at a height of 40 kilometers. Use the physics equation sheet. This looks like we're just using the same blooming, this looks like it's going to be the same Suvat equation. This looks like it's going to be the V squared minus U squared equals 2AS. Seems a bit crazy, doesn't it? We've just used that in a big fat 6 marker. Maybe I didn't need to use it above, but that's the way I did it. The rocket accelerated upwards until it reached 40 kilometers. So it was stationary initially. So we know that U equals 0. Calculate the velocity, that's going to be V, 40 kilometers. We know the constant acceleration was 6.48. So really, we're going to do the same thing here, which is V squared is equal to 2AS. We know that 2 times 40 kilometers, we need to turn this to meters. So that is 2 times 6.48 for the acceleration, but the distance this time is in meters. So I want to write 40,000. So let's do this. 2 times 6.48 equals that, times 40,000 equals velocity squared is huge, 518,400. Now I want to work out the velocity. I'm going to need to square root both sides. That will get rid of the v squared. And I'm going to get 518,400 So let's do it. So on my days, ah, I'm using my mobile phone calculator today, which is really not enhancing my experience, I have to be honest. 518,000, and I want to bust out 400, and that equals 720 meters a second. So the way this is going to work, you're going to get marks for working that out. You're going to get a mark for converting 40K to meters, a mark for sticking all the numbers in, probably a mark for selecting the correct equation, and then a mark for the answer. Oh. Explain how the weight of the rocket changed as it accelerated upwards. So we need to explain, how does the weight of the rocket change as it accelerates upwards? I've got to say, I think this is an unusually hard combined science paper too. Explain how I reckon the grade boundary was quite low for this one because these are some really tough, tricky concepts and questions. Explain how the weight of the rocket changes accelerated upwards. Right. Well, what do we know about going up, height, all that business? Well, we know GPE, gravitational potential energy, is equal to mass times height times G. What do we know about weight and mass? We know that weight equals mass times G. Um, as it's burning fuel. So it tells us, this is really tricky, but in the question up here, it tells us uh, right up here in the stem, passenger module, propulsion module. The propulsion module burns a large volume of fuel. So lots of the fuel has gone. So what we really want to say here is, we don't need this first bit here with the GPE, but we can say calculate the velocity of blah, 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 blah. No, we're down here. Explain why the weight of the rocket. Well, the weight of the rocket changed as the rocket moved upwards, it burned fuel. That's one mark. Fuel has mass. So we can say the mass of rocket decreased. Um, weight is mass times G. So weight decreased. So if you worked out that the weight decreased and you just said weight decreased, you'll get a mark. If you said it's because it's burning fuel and the mass has gone down, you get a mark. Weight is mass times gravity. There we go, 3 mark. God, this is a difficult paper, difficult concepts. Right, at a height of 40 km, the rocket stopped burning fuel. The rocket continued upwards to its maximum height of 60 kilometers. Explain why the velocity of the rocket decreased between a height of 40 km and a height of 60 km. So this is about energy transfer. So the rocket got to 40 km. It stopped burning fuel, so it turned its engine off, but it's still going forward. It's still going forward until it gets to 60 km. But what do we know is happening? It's not burning fuel, so the mass is not changing. We know that kinetic energy is equal to half m times velocity squared. So in order for v to be going down, something must be happening to our kinetic energy. And what is happening? Well, the kinetic energy is changing into another type of energy. As it goes up, it's gaining gravitational potential energy, and the kinetic energy is being transferred into GPE. So the kinetic energy of the rocket is being transferred into gravitational. I can't spell it. I'm just going to put GPE because I'm having issues. It's being transferred into GPE. So kinetic energy decreases. This decreases the velocity of the rocket. Remember, the mass stays the same uh, as it is not burning fuel. So it's not down to the mass. The mass stays the same as it's not burning fuel. But really, some of the kinetic energy is being turned into GPE, and so it is losing some of its velocity must be going down. Do 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 do. What the hell? 6.4. At a height of 60 kilometers, the two modules of the rocket separated and the passenger module fell back to Earth. Figure 10 shows the passenger module falling towards the Earth. Parachutes, passenger module. Using parachutes causes the passenger module to fall with a lower terminal velocity than if the parachutes were not used. Explain why the parachutes allow the passenger module to fall with a lower terminal velocity. Jeez, they love it. Right, or velocity. Well, the parachutes, you can see with these arrows here, the parachutes, so air will be hitting the module, and what will happen is eventually, as the air resistance slows, as the air resistance increases as it falls, you reach terminal velocity when the force of weight is equal to the force of air resistance. And so that takes time to reach terminal velocity. At first, you're accelerating towards the ground. So at first, the passenger module is accelerating towards the ground and air hits it per second. As it increases in its speed, the air resistance increases because more particles hit it per second eventually until the forces are equal. And then it has reached terminal velocity. So at that, I don't know, it might be falling at, 500 meters per second, and that is its terminal velocity. So that's the maximum speed it can fall at. That's the speed at which the air resistance and the downward force are equal. Now, the difference with parachutes is more air particles can hit. They have a large surface area, so more air particles can hit it per second. So what this does is this increases the upward force and the deceleration is increased. So there's a greater deceleration, but as the acceleration is decreasing, and it's actually, well, the acceleration is decreasing. The velocity that it's falling at is decreasing, but eventually, less as it falls slower and slower and slower as the velocity decreases, less particles hit per second until eventually the forces are balanced again. This time it will be at a lower speed though, because of the greater air resistance. There was a bigger drop in the speed than would have been with the passenger module because there's a greater effective area. Anyway, so what we want to say there really is so we want to say larger surface area of parachutes or greater effective area means greater air resistance, more air particles collide per second, um, a greater drop in accelerate, a greater drop in velocity. So there's a greater drop in the velocity of the module before the forces become equal. So terminal velocity is at a lower speed. So you get terminal velocity when the forces become equal because this is that's going to basically they're going to equalize at a lower speed, and that's going to get you your 3 marks. That paper was disgusting. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.